Hello, welcome to this lecture video. So I'm teacher Melai, and today we will be discussing determining the shape of the distribution. So what are the considerations that we need in determining appropriate tests to use in our data? So first, of course, we have to go back to the research problem. So what is our research problem all about? So do we intend to answer simply a descriptive problem, or we will answer inferential problems? And then next, aside from the problem, what is also the shape of the distribution? Is it normal or is it skewed? And then, how many variables are involved in the study? So is it only one, so it's univariate, two variables, bivariate, or three or more, it is multivariate. So for us to determine what appropriate test to use, these are the important things that we need to consider. So whatever is the problem, so it could be simply a descriptive statistics or rather descriptive problems that requires the measures of central tendency, or inferential problems that aims either to compare, to correlate, or to determine the significant predictors or correlation. But in this video, we are going to focus on the discussion on the shape of the distribution, which of course now leads us to the discussion of how to determine the shape of the distribution. So we actually have several ways to do that. So first, we can consider histogram or stem rather and leaf plots. Next, we can also consider box plot. We can also consider measures of central tendency, this computation of skewness and kurtosis, and Kolmogorov-Smirnov test and Shapiro-Wilk test. Okay, let us consider histogram. So in our previous discussions and topics that we tackle, you were asked to come up or to construct histogram. So if you will be asked to make use of several data and come up with histogram, you might encounter some of these shapes. Like for example, the first shape, so this one is called uniform histogram or rectangular shape. This is called U shape. And also another one, so here, this is a J shape, inverse J shape, and this curve. So actually, aside from mentioning the possible or how it looks like, whether it looks like J, it looks like U, or inverse J, we can also describe our histogram in terms of the highest frequency. So just like here, if we have one highest frequency, we call that as unimodal. While if we have two highest frequency, we call it as a bimodal. If we have three or more highest frequency of course, we are referring to the same frequency. And so we call that as multimodal in general. So the J shape and inverse J shape here, and also the last figure is called a unimodal. And then for this shape, it is a bimodal, and also with the second, it is bimodal. For our first shape, our uniform, since we have the highest frequency and it contains only one bar with highest frequency, we call it as still as the unimodal. Okay, so aside from that, we can use this as mentioned in determining for the shape, not only by mentioning that it is rectangular shape or it is unimodal and all other shapes, but we can also use curve to determine whether it is normal or not. So just like our first figure, so if we are going to draw curve, it will look like this. Second figure will look like this, and third figure will look like this. So for the shape of our curve, we call the first figure as negatively skewed, the second figure as a positively skewed, and the last figure as normal distribution. So it is a bell shape. So if we are going to draw a curve to our histogram and it looks like a bell shape, it is normally distributed. Okay, so the next one as mentioned is box plot. So in box plot, if we have a symmetrical shape, just like the first figure, wherein the mean and the median are located at the center, so this is also normal. While for our second figure, so it is asymmetrical with respect to the mean. And of course, the mean and the median here have different values. It is not normally distributed. So it is asymmetrical. So it is not normal. So as mentioned, the first figure represent normal and the second figure represent skewed. Okay, how about if you will also consider measures of central tendency? So remember that you were asked last time to compute for the mean, the median, and the mode. And you can actually make use of that for you to determine the shape of your curve. So if here, so let's use the same figure that we used in describing our histogram. So if the shape looks like this, it is called, as mentioned, it is negatively skewed, and the highest value is the mode, the lowest value is the mean. While for a positively skewed data, the highest is the mean and the lowest is the mode. So you can see here our symbols. M sub O represents the modes, M sub D represents the medians, and X with bar above represent the mean. And of course, if the value of the mean, the median, and the mode are equal or approximately equal, then we say that the data is normally distributed. So that is how to use also measures of central tendency to determine whether the shape of the distribution is normal or not. Okay, let's move to skewness and kurtosis. So what is skewness and what is kurtosis? So these are also ways for you to determine if the shape of the distribution is normal. So skewness is defined as measure of symmetry. So we can determine whether it is symmetrical or asymmetrical based on the value computed. And for kurtosis, it is a measure of whether the data are heavy-tailed or light-tailed relative to a normal curve. So let us just represent that using figures first. So for skewness, so this is the normal or symmetrical in general. And this is one of the symmetrical figure. So it is positively skewed, or we say that it is skewed to the right. And this is the next figure. It is also negatively skewed, or it is also called skewed to the left. While for kurtosis, so this is the figure that represents kurtosis. So we have here a legend that shows that our normal curve, as indicated here by yellow color, is our normal curve. It is called mesokurtic, while The number one here, colored with blue, we call it as a leptokurtic. So it is above the normal curve. And platykurtic, so this is the color green, number 3. It is called the platykurtic. So it is below the normal curve. Okay, so what is the rule of thumb in using this, what do you call this, the skewness and kurtosis? So if the skewness is between negative zero point 0.5 and zero point 0.5, we say that the data are fairly symmetrical. So we can conclude that it is normally distributed. While if the skewness is between negative 1 and zero point 0.5 or between, or rather negative zero point 0.5 or between 0.5 and 1, then the data are moderately skewed. And for number 3, if the skewness is less than negative 1 or greater than 1, the data are highly skewed. Okay, so let us show that using the Microsoft Excel. So how to do that using Microsoft Excel? So we will use a dummy data here. So let's say, for instance, so the following are the scores of the students. So these are the scores of the student. So we are going to check if the data is normally distributed or not. So using histogram, we can just simply select this. But let us consider, for instance, more data. Okay, let's have 20 data. So if we will consider this, insert, let us just try to compute for the skewness. So equal sign SKEW, open parenthesis, and then let us select the data, close parenthesis, and enter. So this is the skewness. So what can you say about the data? So is it normally distributed or not? So we have to go back to our rule. So this is our rule. The rule states here that if the skewness is between negative zero point 0.5 and zero point 0.5, positive zero point 0.5, it is fairly symmetrical. So this is negative 0.14. It is within negative 0.5 and 0.5. Therefore, we can say that our data is fairly symmetrical. We can conclude that it is normally distributed. How about it if we will also consider, let us also consider kurtosis. So let us check for the rule of thumb for kurtosis. So that, okay, so let us search the internet for that value. Okay, so for kurtosis, so we have here a lot of discussion that talks about how to compute for, so this is the formula of skewness. If you will compute it manually, And then, as mentioned here, if the skewness is less than -1 or greater than, so this discussion is already shown in the example. And then for kurtosis, so we have here also the formula. Okay, so let's have the last paragraph. So hence, mean is the sample mean. The -3 at the end of is often explained as correction to make kurtosis of the normal distribution equal to 0. As the kurtosis is 3 for a normal distribution. So let us still look for other reference material for this. So if it is okay, so we have here, kurtosis is a measure of a combined sizes of the two tails. So it measures the amount of probability in the tails. So the value is often compared to kurtosis of the normal distribution, which is equal to 3. So if the kurtosis is greater than 3, the data set has heavier tails than the normal distribution. So more in the tails. If the kurtosis is less than 3, then the data is lighter tail than the normal distribution, less in the tails. So kurtosis is sometimes reported as excess kurtosis. It is determined by subtracting 3 from the kurtosis. So this makes the normal distribution kurtosis equal to 0. So kurtosis originally was thought to measure the thickness of distribution, and you will see that as part of this definition in many places, this is a misconception. Skewness and kurtosis involve tails of the distribution. So as mentioned here also, so if we are also referring now to as to the shape of the distribution, and we're going to use skewness only. So it's also better to use both skewness and kurtosis because of course kurtosis and skewness are both a measure of a thickness of a distribution. So as mentioned in the slide, skewness refers to the symmetrical or asymmetrical, but aside from that, it also talks about the thickness of a distribution, just like the kurtosis. So our reference is the 3. So as mentioned also in our article here, the value is often compared to the kurtosis of the normal, which is equal to 3. So let us check for the value. So how to compute for the kurtosis? So that is equal sign, kurt, equal sign, kurt, open parenthesis, and again, select our data, close parenthesis, and enter. So there you go. It is negative 0.51. It is below 3 or below a negative 3, which means it is also normally distributed. So the value of skewness is supported by the value of kurtosis. So no doubt, this data is normally distributed. So we actually have one more type of distribution, or rather one more way on how to determine for the shape of the distribution. And that is with the use of inferential method, and we call it as Kolmogorov-Smirnov goodness of fit, or simply it is KS test. So we use this to compare data with a known distribution and let you know if they have the same distribution. It is commonly used as a test for a normality to see if your data is normally distributed. It is also used to check the assumption of normality in analysis of variance. So the problem when we are using descriptive way for us to determine whether the shape of the distribution is normally distributed or not. So it might be, for instance, if we will just rely on the shape in terms of drawing the curve. So it may mislead us to say that it looks like normal, or it looks like a skewed, because sometimes when you draw or you construct histogram and try to expand it, or it may look like that it is not normally distributed anymore. It may looks like a platycurtic. Or if you try to pull it up, the figure will be pulled it up because you have used also the range of the, what do you call this, the range of the data that you used for the values, for instance, for the interval that you use for the x-axis or for the y-axis. So it may affect the figure. So whether, and this might affect us in deciding if our data is normally distributed or not. And then if we will also rely on the use of measures of a central tendency and not with figures like histogram or box plot, or the stem and leaf. So it may also be a problem because what is approximately equal to you might not be approximately equal to others. And this again may lead to another problem that you have different conclusion whether the data is normally distributed or not. Okay, so going back here, so this is an inferential way, a non-parametric inferential is statistics that can be used for us to determine if our data is normally distributed or not. Another is the Shapiro-Wilk test. This is also another method or another test that used to tell that is also used for us to determine if our data is normal or not. Okay, so these are the reference materials. So for more details about Shapiro-Wilk and Kolmogorov-Smirnov test, we are going to consider another video for that. So for now, thank you for watching.